on are three problems. And we're going to do, we've done them all from the frequentist point of view, and we want to do them from the Bayesian point of view. So we'll just focus on these three problems. There's, of course, many problems you can do, but these three give you a good taste for what's happening. One of them is to estimate a CDF non-parametric. And we've seen how to do that in the frequentist world. I'll remind you about that in a minute, which is to use the empirical CDF. We'll see that the most common non-parametric Bayesian thing is to use something called a Dirichlet process prior. If you've never seen it before, some of you have seen this before. If you haven't, it'll take a little bit of getting used to because the prior is a little bit indirect. In some sense, we can't write down the prior. Like a normal prior, you can write a formula for it. In non-parametric Bayesian, you can't write down a prior. Or typically, you cannot write down a formula for the prior. But we can tell you an algorithm for drawing from the prior. And having an algorithm to draw from a distribution is sort of computationally equivalent to knowing it. And similarly, you'll see that posterior, you can't really write down a formula for the posterior, but we can give an algorithm for drawing from the posterior. So in that sense, it's equivalent to knowing the posterior. And then for estimated density functions, we did kernel density estimation. The most common Bayesian non-parametric Bayesian method is called the Dirichlet process mixture. And finally, for regression, we saw several methods like kernels and splines. In the Bayesian world, it's Gaussian process regression is the most common. And once we introduce the methods, and once you get your head around what it means to compute posterior, we'll talk about properties of these, like when are these consistent? When does the posterior converge to truth? And then we'll talk about the surprise, which is that it shows up really interestingly here in the regression world that the priors that give you that make the posterior converge to mean actually have some pretty weird properties, very unexpected properties. So it's just kind of intellectually interesting to study these systems as well. So that's the plan. It'll probably take today and maybe a bit of Wednesday, and then after I'm done, Ryan will start, I guess it's a complex optimization you start, Ryan? Complex optimization. Any questions before we proceed? How many of you are familiar with the Dirichlet process? So for you guys, it'll be a little bit of review. So you can jump right here to page 636. And the image that you should keep in mind throughout all of this is that the parameter space in a non-parametric problem is some class of functions, CDFs, densities, regression functions. So it's some infinite dimensional class. And there's going to be a prior pi sitting on top of this. It's a bit hard to picture because I have to tell you that density functions don't exist on quantum space. So we can talk about probability distributions, but not density functions. Another strange thing is that in non-parametric Bayes, it's not always the case that you get the posterior by Bayes rule. That would be surprising. But you can have a well-defined conditional probability for k to give an x, even though Bayes rule doesn't apply. You might think of computing conditionals as equivalent to Bayes rule, but actually that's not true. It's a more general idea. So the whole world is kind of weird, the whole non-parametric Bayesian world. And then, of course, we're going to get some data, and we're going to update this to be some sort of posterior distribution, which will be So you should picture there being a prior over the space of functions and then a posterior over the space of functions, even though it's obviously very hard to picture a function space. So let's start with the first problem, which is estimating a CDF. So we have these random variables, x1 to xn, IID from a CDF, capital F. Remember that the CDF is the probability of the random variable is less than or equal to x. The CDF completely characterizes the probability distribution, right? I have two random variables with the same CDF, then they have the same distribution. And the standard or most common frequentist estimator of the CDF is the empirical CDF, f n of x, which is simply to put a mass at 1 over n at each data point. So there's a probability mass function, and we form the corresponding CDF. which at any point x would be the proportional data points to the left. So that would look like this. It jumps by 1 over n at each data point. So this is 1 over n. Okay, so that's the standard frequentist. It's not the only one, but it's certainly hard to think of circumstances repeating these other ones because this is so simple. And we know some things about this. Jumping ahead a bit, when we do VC theory, one of the things we'll conclude is that the empirical CDF is uniformly close to the true CDF with high probability. And in fact, there's a result that's very famous that's a bit tighter than the VC result, which states the following thing. The probability that the supremum over all x's Fn of x minus f of x being bigger than epsilon is less than or equal to this quantity. That turns out to be something like a VC bound, but it's actually a bit tighter than you would get from VC theory. This is called the DKW inequality. DKW means Dvoretsky, Kiefer, and Wolfowitz. Dvoretsky was a famous Russian probabilist, I think, and Jack Kiefer was a very famous statistician. And Wolfowitz was also a very famous statistician who ended up having a very famous son that some of you may have heard about in the political arena. And this is named after them. And so that tells you the empirical CDF is everywhere close to the true CDF with high probability. And this is true for any CDF, by the way. So we could even, if we wanted to, we could even put here the supremum of all CDFs. So that's a pretty strong statement because the right-hand side doesn't even depend on the CDF. And one consequence of this is we can get a confidence band very easily. Just set this equal to alpha, and you will get epsilon equals something like 1 over 2n log 2 over alpha, I think, which would make this alpha. So what that says is that, therefore, Fn of x plus or minus alpha, or epsilon, that's a 1 minus alpha confidence band for CDF. So in other words, the probability, so let's write it this way. For any f, the probability under f that Fn of x for all x is at least 1 minus alpha. Okay, so that's now a complete story for the frequentist approach. We have a point estimator. We can say something about its convergence. This implies it's a consistent estimator. And you have a confidence band for the whole function. So now we want to say, well, let's suppose we do want to take a Bayesian point of view here. We need to put a prior on the set of all distribution functions. That's a little bit hard to picture again, but it was Tom Ferguson, who's a statistician at UCLA in the 70s, who came up with the following idea. Which was to come up with a prior, which is now known as a Dirichlet process. And so we're going to write it this way. F is drawn from a Dirichlet process. Now this prior has two hyperparameters. So these are extra parameters you have to specify the prior. Just like if I said theta has a normal prior, to specify that normal, you have to tell me the mean and variance of that normal prior. Similarly here, I have to specify two things. And those two things are actually a function and a number. And roughly speaking, this function, f0, is what your prior guess at the CDF. And alpha is, in some sense, your strength of belief, how spread the prior is around that CDF. So what does this mean? Well, actually, I'm going to describe this prior then. There's a couple ways, now many ways to describe the same prior distribution. I'm going to describe two different ways to think about this prior distribution. So again, I can't just say it has the following density function, because there is no density function over the set of distribution functions. So I'm going to describe two different ways to think about this prior. One is an algorithmic method to say, well, suppose I wanted to draw a distribution function from this prior distribution. This is a prior. So what I'm saying is I can't mathematically, in some sense, describe phi to you, but if I wanted to take a random draw from the prior, here's how you do it. And most of you are computer scientists, so that should feel very comfortable. I'll give you an algorithm, and for drawing from something, that's better than knowing what it is, in some sense. Right? Not quite, but you know, that's almost the same as knowing what it is having an algorithm to draw from. And this algorithm is called the stick breaking representation, and it's pretty cool. So it works like this. So again, what I'm describing is an algorithm to take one random draw from this prior. What I'm going to give you is a CDF when we're done. So in the space of CDFs, when we're done this algorithm, you're going to have a single CDF. And the algorithm looks like this. It's kind of a pseudo-algorithm because you couldn't actually implement it as I'm saying, but it's sort of close to being an algorithm. Because what you have to do is, first of all, draw an infinite sequence of points, IID, from F0. So in practice, you can't draw infinitely many points. But there are actual algorithms that people do where you just do a large number. You just do 1,000 and you stop or something like that. So practically speaking, we can't draw infinitely many. But just conceptually, let's imagine drawing an infinite sequence of these. Okay? The second step is to draw another infinite sequence of random variables. V1, V2, V3, IID from a beta distribution with parameters 1 and alpha. So let me remind you what a beta is. A beta density is proportional to, well, in general, a beta density. Well, usually, I mean, I should have written that. Okay, anyway, I'll tell you what it is. It's, what is it? Does anybody remember what that is? Is it 1 minus v to the alpha minus 1? Does that sound right?
To the beta.
Yeah. Okay. That's just some density on 0, 1. Looks like this. No, I did it wrong. I knew I was going to do that. So looks like this. If you forgot what a beta density is, you should review that because everybody should know what a beta density is. Even I'm going to forget. It's a density on 0. Okay, so now we've done these two things. We've drawn a set of real numbers from F0 and a set of these betas. Now what we do is we start what's called the stick breaking process, which works like this. We take a stick of length 1, and we take our first v. This is a beta random variable, so it's between 0 and 1. And we declare w1, a new variable w1, to be equal to v1. What we're doing is we're saying, okay, I've broken off a piece of this stick. And now we create a second weight, w2, which is we take v2, which is a number between 0 and 1, and we take that proportion of what's left over of the stick. So w2 is v2 times 1. Right, so now I've broken off this piece of the stick, that's w2. And you keep going. So you take the remaining stick, and v3 is a number between 0 and 1. You take that proportion of this, and that's w3, etc. And so in general, if you write this down, you'll see that in general it turns out that you can write wj as vj times the product of the previous j minus 1, 1 minus 1, and so on. That's That's now an infinite sequence of W's.
Can that be the product of 1 minus pi?
It should be. Thank you very much. Hopefully I got it right. And now after all of this, one thing you'll prove in the homework, it's not too hard to prove, and we give you lots of steps, is that these numbers, and you can kind of see it from the picture, sum to 1 with probability 1. I think you can see that, right? I see the chunks of it. I'm literally breaking up this stick and keep going, and you eventually get the whole stick. So these weights sum to 1. Yes?
So the reason why we don't just normalize the V's and break the stick just in proportion to the
You
V's?
could do that, and that would define a new prior. However, so this, remember, I'm trying to give you an algorithm for this particular prior called the Dirichlet process. But as soon as you see this construction, you can see there's other things that would help you to generate a random CDF as well. You'd just be inventing a new prior distribution.
Is there any specific reason why we go with this formulation?
Well, so that gets to the question of why do we want to use the Dirichlet process prior. And the reason is mainly because it's commonly used, it's easy to understand, and there's lots of properties proven about it. But it's certainly not the only prior. Okay, finally, here's what I do to make, remember I have to draw a random CDF. How do I get a CDF out of this? What you do is you take these numbers, so let's say here's S1, and you put a point there, and then you take W1, which is a weight, and you put a toothpick with that weight there. So let's say that's S1. Now you take the second number, S2, so maybe that's here, and you put that weight, W2, here, and you keep doing this. You're going to get countably many toothpicks, but they sum up to 1. And that defines a mass function, and in particular then it defines a CEF, because at any point I just sum up all the mass to the left. So I define f of x, now my random f of x, to be the sum of wj, and this is a point mass at Sj for all Sj's less than or equal to x. So it's going to be a very wiggly CDF, right? There's a lot of little jumps there. In fact, one thing to notice immediately about this is that it's discrete. When you draw from this distribution, from this prior, you get a CDF that's discrete. However, despite that fact, this prior does fill up the space in the sense that if I take any CDF, even the continuous one, and you look in a neighborhood around it, you'll find that there's always positive mass, this prior with positive mass in some sense around that CDF. Just, you can think of the discrete CDFs as being dense in the set of CDFs. So I want to make sure that this algorithm is clear. Any questions about the algorithm? Again, what this is an algorithmic description of a Dirichlet process prior. If you did this algorithm, you would get one CDF, and that would be one draw from the prior. And if you wanted to sort of understand the prior, you could do this algorithm many times and then look at the CDFs you get out and say, oh, okay. Just like if you wanted to understand a normal, you could draw 100 observations from a normal, look at the data, and that would give you a feeling for what a normal distribution is like. Similarly, you could draw many random CDFs from this prior, and in some sense, that would give you a feeling for what this prior looks like. And that's the prior. Now, I want to take the prior and go from the prior to the posterior. Unfortunately, as I said, Bayes' theorem doesn't work, which is maybe surprising. But there are conditions you need for Bayes' theorem. But how can I talk about a posterior if I can't do Bayes' theorem? Well, here's why. I'm not going to do the measure theory, I'm just going to give you the intuition. That we have, if you think of f as a random variable, it has some distribution. But we also have a distribution for the data given F. Namely, these are IID draws from F. So if I have a distribution, let's just think more abstractly. If I have a distribution on some object theta and a distribution on some other object x given theta, that defines a joint distribution, right? Theta and x. So there's a joint distribution of theta and x. But whenever I have a joint distribution, I can talk about the conditional distribution of one given the other. So I can, from that, talk about the distribution of theta given x. So without doing Bayes' theorem, we can still meaningfully talk about the existence of the distribution of the parameter given x, which in this case would be the distribution of x given x1. In fact, a lot of Ferguson's paper is proving this, that there's a well-defined posterior and whatever is profitable. So I'm not going to prove, I'm going to tell you what the posterior is, we're not going to prove it. Question? No? Okay, so again, we have a prior, we get some data, and now you do Bayes' theorem, with quotes around it, meaning we update to get the posterior distribution. And here's one of the nice properties about the Dirichlet process, is that it can be proved that the posterior distribution is also a Dirichlet process. So, does anybody know, what is it called when the posterior and the prior are in the same family? It's a conjugate situation, right? This is a conjugate prior, because the posterior is in the same family. This is a Dirichlet process, and of course the parameters change. So alpha becomes alpha plus n, and F0 gets changed into, I'll call it F bar n, where this is actually the mean of the posterior. So F bar n is the expected value of the CDF given the data, and it's explicitly given as this thing. So what is that? That's just a convex combination of the empirical CDF and the prior CDF. Makes good intuitive sense. And in fact, you can see as n gets large, this starts to dominate and the prior gets washed out. So it sort of has very nice intuitive behavior. And now, if I want to answer, I don't know, a question on the homework, for example, that would say, draw a 95% confidence band for CDF, you can now do it, because here's how you would do it. You'd say, well, okay, I'm going to draw a large number of times, let's say capital N times, from the posterior. We don't know how to write down the posterior, but we can draw as many times as we want from it using the same algorithm. Of course, alpha becomes alpha plus n, and F0 becomes Fn. But otherwise, we can draw many times, and so you would get this, let's say 10,000 draws. And now, you can find a pair of functions which contains 95% of the draws. And that would give you a visual representation of the Bayesian 95% band. That band would have the property, let's call that L and U, that the posterior probability that F is between L and U for all x, given x1 to xn, is 1 minus L. And to remind you, we talked in grade length last week that doesn't mean it's going to have 95% frequentist coverage, right? This is a different thing. So to answer the question about why the Dirichlet process, well, one reason is you can see it's very easy to deal with. It has very intuitive behavior. We can't write down an expression for the posterior, but we can draw as many times as we want for the posterior very easily, and therefore we can keep anything we want for the posterior. So it's very easy to deal with. And it's certainly not the only prior on the space of all CDFs. In fact, there's infinitely many such priors. But I would say that it's the most commonly used one in this situation. Probably because it's easier to understand and it's easy to work with. So there you see the parallel story. You have the frequentist estimator and its confidence interval. And now we have the Bayesian version, which involves the prior and then getting the posterior and computed everything from the posterior. But I want to tell you the other interpretation of Dirichlet processes, which was the original one that Ferguson used. And maybe it's the one you were taught, if you've seen this before. It's a little bit less constructive. So I like the stick-breaking explanation because it's very, very concrete and constructive. But the way Ferguson did it was in terms of what are called Dirichlet distributions. So that makes some sense given the name. Let me remind you what a Dirichlet distribution is. Suppose you want to draw a random vector from the simplex. So the simplex here is a set of all vectors P, let's say P1 to K, let's sum up to 1. Is there a natural density function on the simplex? And the most commonly used density function when people are dealing with vectors like this is a probability vector, right? Because it's positive and sums to 1, is the so-called Dirichlet distribution, which has the following density function. Its f of p is proportional to the some horrendous constant of that we don't care about. And then it's p1 to the alpha 1 minus 1, p2. It's just the multivariate version of the beta distribution. So this is a distribution. It depends on some parameters, alpha 1, alpha 2, up to alpha k. Given those parameters, it defines a density on the simplex, and it's a well-defined probability density function, and lots of properties are known about the Dirichlet distribution. It's commonly used density function when we're dealing with multinomials. So given that, and given the name of the Dirichlet process, you think, well, there must be a connection between the Dirichlet process and the Dirichlet distribution, and here's the connection. Suppose, again, we want to understand what this means to say f as a Dirichlet process distribution. Oops. I've noticed I'm switching the order of alpha and f back and forth. I hope that's not terribly confusing. So, imagine somebody has the ability to hand you a random f. Of course, we just talked about a method for doing it. But even if you've never heard of that algorithm, you could say, suppose somebody gave me a randomly drawn f. What properties would that have? And here's an interesting property that it has. If I take any partition, finite partition, of the real line, and I compute the probability content of those elements of the partition using the f you just gave me, so that gives me a vector. Let's write it like this. So you give me a random f. I compute these numbers that sum up to 1. That gives me a random vector. And it turns out that random vector has a Dirichlet distribution. And the parameters of the Dirichlet are related to the f0 and alpha. That's a detail. So in other words, in some sense, the projection of f onto any finite partition is a Dirichlet distribution. That's why it's called the Dirichlet process. And it happens for every partition, and it happens consistently in the sense that if I took another partition and divided that, this Dirichlet marginalized to the bigger partition would give you the same distribution and so on. It behaves in consistency. So that's the way Ferguson originally described it. You can think of it as, again, if I evaluate my CDF in any finite partition, I get back a Dirichlet distribution. But I don't know. It's good to know both ways of thinking about it, but I find the stick-breaking one just very constructive. Yes?
F doesn't have to be measured.
It is. F's a CDF. This is a CDF. When I write f of a, so I'm using notation a bit, I really mean the integral over a1 with respect to the distribution f.
Yeah, on that same note, this doesn't have to be necessarily defined on the real line or on
the way I've described it, it is, although you can certainly extend it to other spaces. But traditionally it's defined on the real line.
Is the stick the same thing ordered? So is this the stick breaking thing that we did? Was it these same partitions ordered on the basis of the magnitude?
No, there is no
between the two?
partition, right? In the stick breaking thing, there's really no partition involved at all. In fact, you're getting counted infinitely many little points there.
But even if we just went on infinitely into partitions, it would actually have the.
Oh yeah, their
image
two
of-
definitions are consistent with each other. Absolutely. All right. Any other questions? All right. Now, let's talk about Bayesian non-geometric density estimation. This is a little bit more complicated. Suppose I have x1 to xn from some distribution which has a density f, and we want to estimate the density. So there's many ways to estimate the density function. Let's just remember that in this class, the one we emphasized from the privileged point of view was the kernel density estimator. Again, I'm going to stick to one dimension to keep it simple. So in one dimension, remember that looks like this. And that was our kernel density estimator, and there was that problem, remember, of choosing H carefully to get it. So, what is the natural analog of Bayesian method? Well, there's actually a few different routes, but the most common one is what's called the Dirichlet process mixture. Which works like this. And this was invented, by the way, or discovered, I don't know, by Michael Escobar, who was a student at Yale. He actually came here for a few years. He's at the University of Toronto now. And this was his thesis under the direction of John Hartigan, who was famous for creating lots of interesting things. And the idea is this. So first of all, we start with some intuition, which is if I want to create a kind of flexible family for doing density estimation, one thing that might come to mind are mixture models. We saw mixture models. They're complicated, but we saw they are flexible, right? And so one thing you might do is a mixture model with, say, k mixture elements, and then put a prior on k. The Dirichlet process tries to kind of finesse that a bit, tries to avoid having a prior on k, or at least does it more implicitly. If you think about a mixture model, what's happening is that some observations are coming from one normal, let's say a mixture normal. Some observations are coming from one normal, some observations are coming from another normal. Is there a way to kind of model that more directly? And the answer is in the Dirichlet process mixture, which some people mistakenly call a mixture of Dirichlet processes. That's not right, because that would be a mixture of Dirichlet processes. This is using a Dirichlet process to create a mixture. It works like this. Actually, let me go back for a moment. One of the criticisms people have of Dirichlet processes is the fact it does produce discrete distributions, and some people don't like that. But here, it's actually going to turn out to be a virtue. Because what happens is this. We construct this prior in what's called a hierarchical fashion. So we imagine drawing some distribution f from the Dirichlet process. And again, there'll be two prior parameters. We'll come back to this in a minute, but there's going to be an f0, which is a CDF, and an alpha, which is a number. But now, we don't draw the data from f, like we just did. We draw these intermediate variables, theta1 to theta n, so given f, are drawn from f. So let's think about what that means. I'm going to draw n real numbers from f. So I draw this random distribution function first, which is, we saw very wiggly. It's discrete. Now I take n draws from this CDF. Now, here's, if you think about it, what happens when you draw from a discrete CDF? And by the way, remember when we put those weights down, W1, W2, W3, and so on, it's not hard to see that the first two weights tend to be very big and then they die off pretty quickly. So not only is this a discrete distribution, but it's got sort of a few big things and then some smaller ones and so on. If I draw many times from this discrete distribution, I'm liable to get ties. I'll probably get a few from here, a few from here. Okay, so I'm drawing these, I'm writing them as n draws from F, but keep in mind that many of these thetas are going to end up being the same. We could get 3 draws from this one big chunk and 2 draws from here. And that's exactly what you want for mixture models. That's telling you the clustering. That's creating automatically a kind of clustering property. But now I still have to draw the data itself, and what we do is we take each xi given theta I is a draw from some distribution. And the most common example is that this would be a normal. So really, theta I you should think of as not being a number, but probably it's going to be a vector, like a mu I and a sigma I. Specify normal. But just to keep it simple, let's just think of it as a single number. So this is the, see, we're creating a mixture distribution because the x's given the thetas are normal, but many of these normals are actually the same. So I could rewrite it as, some of them come from one normal, some of them come from another normal. I've actually created a kind of hidden mixture model here. And the alpha parameter controls how clustery it is, the number of expected clusters you get as a function of n. Notice that as n gets bigger and bigger, you can prove, in fact, that the number of clusters you get is increasing. And how the number of clusters changes as n is something people have investigated. It depends very much on this parameter alpha. So this is kind of cool because I've kind of described, again, in almost an algorithmic way, what the prior setup is here. Now, how do you get the posterior? Well, now it gets a bit complicated. Again, it's the only way to get it is through sampling, and there are what are called Gibbs sampling algorithms, which we'll talk about later in this course. For drawing random densities, now you can draw as many times as you want from the posterior distribution. So once again, we're not going to explicitly write down a formula for the posterior. We're just going to say it's some sort of posterior distribution of all densities. But there is an algorithm for drawing them. And so you can draw them and look at them and so on. Now, I'm not going to go through the details, but it's actually a bit painful. I mean, none of the steps are terribly hard. You have to derive each thing. You have to figure out how to draw the thetas, given the alpha, and there's all kinds of steps involved. Right? And I think it's not that interesting for us here. Just I think you'll trust me that there exists a algorithm. At some point, I spell it all out later on the notes. There's a subsection called the detailed. Well, actually, even that doesn't spell out. It's non-trivial to do this, and in fact, I've left out part of the story, which is to tell you more about this. But let's, for the moment, just pretend again that this is fixed. I want to make sure that the model is clear. If I did this, right, I would end up with a finite set of thetas, and you can think of it as a mixture of normals now with those means today. Is there any question about the model?
So the densities that you're actually are normals?
Well, so you can actually don't have to be normals. They can be anything. But the most commonly used one is normals. But actually, you can put in any geometric theorem you want. Again, an alternative would be to explicitly say, no, I want to do a finite mixture. J equals 1 to k, and try to estimate k treated as a parametric drawing. Which one's better? Depends a lot, I think, on people's taste. Some people don't like having to put the number of times as another parameter and then put a prior on that. which is what you'd have to do, to do Bayesian inference. And this sort of sidesteps it. On the other hand, some people say, yeah, but here it's kind of hidden. It's kind of built in, whereas here you have explicit control over it. So you can argue either way, I'm sure some people prefer one. Okay, so Matt, yes?
I didn't understand what you said you would get ties and that would create, that's why you get a clustering thing. So what is going to get tied?
These thetas are drawn from a discrete distribution.
Right.
So it might be that theta 1 equals theta 2 equals theta 7. They will not necessarily be distinct. Theta 4 might be the same. Theta 6 might equal theta 17 or theta 21. And those are the clusters. You can think of it now as some normals. 3 observations from this normal, 2 observations from this normal. Okay, so we have the prior. We can draw from the posterior. If you wanted, by the way, if you wanted to say what's the my estimate of the density for the kernel estimator, well, you could say, how about the mean of F given the data? I don't know any formula for that, but I have 10,000 draws from the posterior, so I just take the average. So I could just approximate that by 1 over m times fj of x, where these are drawn from the posterior distribution. That would be a simulation approximation. That would be what you would do instead of doing the kernel. The part I've kind of covered up is, how would you ever pick in particular F0? What prior CDF are you going to have on a set of data? So what people do in practice is they usually put another layer on the prior. This is where it starts to get a little bit baroque. So you might take, for example, F0 to be a normal for some mean theta and some variance sigma squared. But now this has parameters. And so you need to put priors on those. So you get quite a long list of priors. And that's what's on page 644, what I call detailed implementation. This is not I'm not saying this is the optimal one. I just picked one because it was very explicit. This is from a nice paper by Ishwan and James in 2002, where they at least do the very nice thing of very explicitly telling you what their prior is. So they do this, then they take a normal prior on theta, and B, they fix at some number. Then you also need a prior on alpha. And so they take alpha to be a gamma distribution with parameters e to 1 and e to 2, and so on. You need quite a few layers. Otherwise, it won't have enough flexibility, right? If I just took a fixed F0 up there, it's not going to be a flexible enough model. And once you've made all these choices, you now have a completely specified prior. And in fact, then in this paper, what they do is they go through and tell you very precisely, very detail, how to draw from the posterior. Because a lot of the work is figuring out the algorithm to draw from the posterior. So I don't want to go through those details. I just want to make sure that the concepts are clear. That now we have effectively specified a prior distribution over the set of all densities. We now have a way of getting the posterior distribution, or at least drawing from the posterior distribution. And yes, there are some parameters that have to be set. There's quite a few hyperparameters you have to pick. But once you pick them, it's all sort of well defined. So barring the computational details, at least conceptually, I want to make sure that that's clear. Are there any questions?
Are there any justifications for all the priors that you pick?
Well, is there any justification for the priors? There could be 2 types of justifications. Well, there could be 3 types. One would be convenience. One would be, hopefully, if you're doing Bayesian inference, it's because you're trying to represent some prior information, and you're hoping this does represent somehow your prior information approximately. The third one would be perhaps these things have good frequentist behavior. And we're going to talk about that. We're going to ask the question, what is the frequentist behavior of these Bayesian procedures? We're going to get to that at the end of the class, so we're going to be doing the pointers. But a lot of tools we use, right, it's because of convenience. This is a convenient way to do it. It might seem somewhat complicated, but it's probably one of the easier ways of doing it. And once you code up the simulation, it's not that difficult. Any other questions? Ryan?
Larry, to get those weights pi j to go down up there, that's another stick breaking process, right?
No, I was saying this is an alternative, would be to do a finite.
But in any case, you have to draw weights to get.
Well, then you do the Dirichlet, this would be a finite if you just use the Dirichlet prior. All right, so CDF, density estimation. Density one was a bit messier. Let's get back to a cleaner one. And this is going to be a little bit more satisfying, which is non-parametric regression. There's actually a couple of convenient ways to do non-parametric regression. So again, I won't review the frequency methods because we just did them, right? We know there's kernel estimators, local polynomial estimators, spline estimators. Similarly, in Bayesian inference, there's lots of different ways of doing it. I'm going to talk about two. The first one is probably the most popular one, which is called Gaussian process regression. So the problem is this. I have yi is, say, some function. To keep it simple, let's say one-dimensional. So we have a one-dimensional x. And I have y as some unknown smooth function of x plus epsilon I. I equals 1 half. And we want to estimate the regression function m. So again, one of the challenges here in Bayesian inference is to think of a way to put a prior on the space of regression function. So now this is the space, let's say script m, or this is a typical regression function. This is no longer a CDF. It's no longer a density function. It's just some real value function. So in some sense, this should be easier because there's no restrictions on it. Hopefully, we'd like to make it smooth. And that we'll see we can do. So the prior we put on it is called the Gaussian process. Okay? And so then I create a production with an annotation for that. But I'm going to write it like this. M is from, I don't know, let's call it, oh, well, I called it normal, which is maybe a bit smooth. Okay. But what does that mean? Because m is a function. So what we're talking about is a random function. So again, imagine that somebody has put this prior pi on here, whatever it is, and I say, give me a random draw from the prior. Well, what are you going to get? You're going to get a random regression function, a random function. And this prior is called the Gaussian process prior because this random function we're getting, here's the random function, it's not just any old random function, it's called a Gaussian process. What's a Gaussian process? A Gaussian process means nothing other than if I take this randomly drawn function and focus my attention on any finite set of points, the resulting distribution is a multivariate normal. So in other words, if I pick, let's say, this point, and I look at the value of the function, and now suppose I ask you to repeat the experiment. So you start drawing randomly from the prior, give me a new function every time. I just get a number each time. And if I drew the distribution of that number, it would be normal. And now suppose I pick 2 points, 2 arbitrary points. This one, this one. Every time you give me a random m, I evaluate the function at those 2 points. And if I repeat that many times, I'm going to get a bivariate. And so on. If I pick 3 points, I get a trivariate number. So a function with that property that every finite dimensional marginal is normal is called a Gaussian process. And there's interesting theoretical questions about, is that well defined? Does it exist? The answer is yes, it is well defined and it exists, but we'll just take that for granted here. But like any normal, in an ordinary normal, there's a mean and a variance. So here, there's going to be some parameters. These parameters are a bit more complicated. Mu is a function. Not surprisingly, it's the mean. So what that says is if I fix, the x is not random there. If I fix an x and draw a random m and evaluate it, on average, I'll get some function mu, and that's the mean function, which in this setting is often taken to be the zero function. But we also have to specify this thing. This is actually a function of two variables, and it's nothing other than what's called the covariance function. It's just telling you the covariance between m of x and m of y. So in other words, imagine drawing m randomly and computing it at 2 points. They'll have some covariance. This is what this k is telling you. In fact, for those of you who are familiar with Mercer kernels, this is exactly what Mercer kernels. Did I hear a sheep or something? We are about to do the ritualistic sacrificing of the goat before we eat the posterior. Now, again, the devil's in the details, which is that to specify this, this is usually taking some sort of functional form with parameters in it. So there's going to be, k of xy is going to be given like e to the minus beta times something times this plus alpha times this, and then there's going to be parameters there that also get large on. And that's how you're going to control the smoothness. That's going to take the place of putting a bandwidth. I'm going to omit that because that's detail, but it is important because the specification of this kernel function is what controls the smoothness of your estimator, and so that's akin to choosing a bandwidth. But it's not hard to show that the nice thing about this is that if we assume that the data are normal, so if I assume the epsilons are normal, and if I put a normal Gaussian process prior, not surprisingly, we get the posterior is also normal. That is a Gaussian process. And that's one of the nice things about Gaussian process priors. And it's not even that hard to work out what the mean is, and I'll just tell you the answer. The mean, which is equation 2754, so the expected value of m, given, it should do it, I don't know why I wrote y there, it should be all the data, turns out to be, this is now, I should use a different font, because that's the matrix ij of kernel values. Anyway, it's k. And m hat is k times k plus sigma squared. Sigma squared is the variance of the residual times y. And I hope that looks familiar because it's nothing other than a linear smoother. Right? It's some matrix times y. So this in some sense is very similar to the kernel regression or spline regression because we get at the end another linear smoother. Even though it seems that, the conceptual foundation is quite different. The end is easy. How do you show this? Well, to show this is very simple because the properties of this process are determined by its properties on any finite set of points. So just pick any finite set of points. You're back to a normal prior, a normal likelihood, and you just do the usual normal calculation and you convince yourself that you get a normal posterior on that finite set of points, and therefore the posterior is without sigma. So it's just the usual normal calculation.
Isn't k sigma square I inverse? I'm sorry, is it the formula is k to sigma square I inverse? Or just, is it an inverse or?
Inverse, yeah.
That's,
Yes. So So the nice thing about the Gaussian process prior is that we can compute the posterior a bit more easier than in the other, the density estimation and the CDF. A little bit more explicit. Okay. Great. So now we have a taste for what the Bayesian version is of all these frequency things. I'm not doing any of them in great detail because I think, you know, if you're interested, they're easy to look up all the computational details. So I want to make sure just conceptually we understand what's going on in these cases. Because what I really want to talk about is what are the properties of this thing. So we can step back and not say, my friend did this Bayesian analysis, came up with this estimator, but forget how they got it. Now they have an estimator. What's its properties? We can still ask what the properties are. And so we're going to kind of step back and look at these properties. I'm skipping over, by the way, a section about called estimating many multinomials. In some sense, that shouldn't be in this kind of because this is the kind of thing you might have seen for document modeling and so on. I'm not sure if that should be called non-parametric Bayes or multinomial Bayes, I'm not sure where that belongs. But anyway, we're going to skip that now. Go right to page 651. So one of the theoretical properties of non-parametric Bayes. And there's some cool, interesting things that happen. So this was, I have to say, an interesting story for a while that people started to come up with these non-parametric Bayesian analogs to these things, but then for a while it was a little bit mysterious. What are the properties of these things? And there was a little bit of confusion for us. It took a while to sort it out. And we're going to ask kind of 3 layers of questions. Layer 1, which is the easiest one, is consistency. What do I mean by consistency? If this is, let's say, the set of all densities, and if I give you, suppose this is the true density, F0, so let's say I generate a stream of observations. You can imagine doing this on a homework. I take a density, you know, I don't tell it to anybody, and I generate 1,000 observations, and everybody gets 1,000 observations from the density. I ask you, compute the posterior. So now you're going to you take your prior and you get the posterior, which you think was living over here. And we can ask, is it consistent? What do we mean by that? We mean if I take any neighborhood around the true density, does the posterior accumulate in that neighborhood? We'll be a little bit more precise about that in a minute. And that's the consistency question. We'll answer that one first. And this is very well understood now. Then we'll ask, how fast does it converge? Does it converge to the minimax rate? And there's where we'll see an interesting surprise. Something mathematically kind of curious. And then we can ask about coverage comparisons. Remember we talked last week about when the Bayesian things that are 95% to 95% coverage. We saw sometimes that they're quite different. Is this the case where they're different or the same? It's not. So we'll get to that. So let's start with the consistency question. Well, the story actually here begins with a bit of a misunderstanding. At first, there was this belief that Bayes procedures are always consistent. And it's due to this thing called Doobe's theorem, which goes back to 1949. Joe Doobe was a very famous probabilist. And somebody noticed that Doobe's theorem seems to imply that posterior is always consistent. And what does that mean? That it says this, that if I look at the posterior, so let's look at this picture. Let me draw it again. Here's the true density. Take any set A, any set you want. It could either contain F0 or it might not contain F0. Okay. Let's now compute the posterior probability of that set A. So I'm just going to write this like pi n of A. I just got tired of writing given x1 to xn, so the pi n means the posterior. So that's a number. Now what would we like this to be? When n gets large, we'd like that number to go to 1 if A looks like this, or 0 if A looks like this. In other words, we'd like this number to converge to the indicator function. We'd like this to be equal to the indicator for whether the true density is in A, or at least in some limiting sense. I'd like to say that the limit as n goes to infinity, if that's true, that the probability of that is 1. So let's try to unravel this because there's a lot of probabilities within probabilities here. But I just give you a stream of data. You get a posterior probability for a set A. And hopefully for large n, that number should either be 1 if A contains the truth, or 0. That would be a sense in which it's consistent, right? Very strongly consistent. But this is all random. So Dup's theorem says the probability that this happens. So what's the probability over? Well, you have to imagine every possible infinite sequence that you could get. That's a probability space. And the set of all such sequences, some of them this happens, some of them don't. The ones that it happens are not probability 1. I realize that's a little bit of a mouthful there, but hopefully you get the idea that this Dup's theorem is saying that it does converge with probability 1 to the integer. That would seem to settle it. Right? Except I'm going to now show you it doesn't. And it all comes down to what we mean by consistency. The interesting thing about when we start to talk about Bayes is there's so many layers of probabilities. It can get confusing about which probabilities we're talking about. So here's a little example that I think will clear everything up. I'm assuming you're a little bit confused now. So let's take y1 to yn from a normal. Now you have a friend who's going to do Bayesian inference. And by the way, Dup's theorem applies for parametric or non-parametric, so it's very general. So I'm going to do a parametric problem. Normal. Now you have a friend, let's say your friend is very stubborn, and very, very sure of himself, and very wrong. We all know people. So he says, I'm going to put all of my prior mass on 0. I'm putting a point, I'm sure it's 0. That's a legitimate prior. Okay. What is the posterior after you get 100 observations? It's a point mass of 0. This is a prior that doesn't change. Posterior is always equal to the prior. Okay. Now suppose the true value was 3. Is this posterior consistent? Is this putting probability 1 on any set that contains 3? No. It's inconsistent. But doesn't that violate Dup's theorem? We have an example of an inconsistent prior. And the key is that Dup's theorem is stated, this P is with respect to the distribution induced on the data by the prior in the model. So you have theta drawn from pi, and you have y1 to yn given theta drawn from fy given theta. That creates a marginal distribution for the data. Namely, let's call it, maybe I should call it mu, y1 to yn is f of y1 to yn given theta averaged over the theta. This is from your obstinate friend's point of view how the world works. Nature draws theta from this prior and then draws data from that distribution. Well, from that point of view, theta is always the true value. The only data you can get are data from a normal 0, 0, 1, and he's right. It's converging to the truth because he's putting all this distribution is assuming effectively that the prior is correct. This is the distribution y would have if the prior was correct. It's kind of a solipsistic analysis. You know what solipsism is? Branch of philosophy where you believe that only you exist and every the rest of the universe is a fantasy. There's some sort of thing in your imagination. So Dup's theorem, it's a very interesting probability, by the way, theorem, by the way, in probability theory, but as applied to Bayesian inference, it's actually not very helpful because it's saying that this is a consistent posterior, but it is only consistent if the truth happens to be agreeing with the prior. So that's kind of not really capturing what we want. Right?
Would it also be consistent if the prior use had non-zero mass over the...
So that's what we really want to prove. The answer is Dup's theorem doesn't quite do it. So luckily we do have better theorems now, or more appropriate theorems, I should say. I just wanted to get Dup's theorem out of the way because sometimes you'll hear people say, oh, Bayesian inference is always consistent with Dup's theorem. That's not quite right. So The correct theorem is, roughly speaking, it gets kind of technical, but I'll just give you the main flavor of it, which is this. The reason why this posterior, well, it's just what you said. The reason why the posterior fails to be consistent here is there's no prior mass around the 3. So obviously, it's not fair to expect the posterior to be consistent if you're not putting any prior mass in the shoe. So around the 80s and 90s, a series of theorems emerged that said basically the following thing. Instead of saying that the posterior is consistent, it says when is the posterior consistent? And it says if you put, anytime you have a density F, which is in the support of the prior, then you get consistency. What does being in the support of the prior mean? It means that suppose that for every epsilon greater than 0, the prior mass in a ball size epsilon is positive, where the ball is in terms of pullback-Leibler distance. I think you've seen pullback-Leibler distance before, but if you haven't, it's just a kind of a pseudo distance. It's the set of all densities G such that the integral of f log f over G is less than or equal to epsilon. So for those of you who haven't seen it before, this is like a this thing here is like a distance function between f and G. And we're just saying, look at all the, it's a pretty strong distance stuff. If G is a little bit different than F, it'll be really far in pullback-Leibler distance. It's very sensitive to tail. So it's kind of a small neighborhood. Think of it, this is a very small neighborhood. So we find the set of all things with an epsilon of F, and we say, does your prior have a positive probability? And then the answer is, if that's true, plus one other technical condition, which is quite technical, and I'm not going to state it, then we do get consistency. But not as strong as Duke thinks. It's not for every set A. It's only for other neighborhoods. But here's the weird thing. It's not Kullback-Leibler neighborhoods. There's another type of neighborhood. All right? You can see this is starting to get a little bit complicated. Consider the set of all densities. I'm going to call this now A, G, that are epsilon close to F in a different metric. The metric looks like this. It's the square root of F minus the square root of G squared square root. It's the L2 distance around the square roots of the density. So this might seem an odd thing. This is called the Hellinger distance. How many people have seen Hellinger distance? Not too many. It doesn't come up in CS as much. In statistics, it turns out it turns out to be, in many cases, the right distance, which has certain wonderful properties. And this is an example where it just emerges as sort of the right thing to use. But the important thing to know is it's just a distance between densities. But it's a different distance than the one here. And the conclusion, the main theorem of consistency of Bayesian inference is, if you put prior probability in Kullback-Leibler neighborhoods, then the posterior probability of any Hellinger neighborhood goes to 1. The next probability 1. It's kind of strange because you're using two different topologies, one to describe the prior, one to describe the posterior, but it turns out you need to do that. This is why it took people a while to sort all this out. It's a little bit solved. Yes.
So just for general, is it because both Hellinger and Kullback are Bregman divergences? Is there a...
I don't think it's linked to the fact that they're Bregman divergences, as far as I know. This is just the reason why, well, you know, if we went through the proof, which I don't think we will, it just is sort of what you need to make it work. And yeah, it's just sort of what you need to work. But the conclusion is that this is a pretty satisfying type of converter. Saying that you're putting a lot of probability in the Hellinger neighborhood is a good thing. It's not a weak statement. It's a pretty strong statement. So it's what we want. requiring that you put positive probability in every callback library, but it's a little bit stronger actually than you might want, but it's not terrible. And it is possible to construct priors that do this for a lot of different Fs. So in some sense, that's kind of the, there's been many advances actually in consistency since these theorems, but this is really the main meat of all this stuff. That there are reasonable conditions on the prior you can put, which will guarantee you a reasonable version of consistency. So in a certain sense, consistency is settled. And there again, there are refinements. And a lot of people, when they do certain Bayesian, non-conventional Bayesian inference, what they're doing is when they'll write a section on the theory where they check these conditions. They'll check the conditions to ensure that they're getting a consistent posterior. Which can be, in some cases, very easy, and in some cases, very difficult, depending on the situation. The condition, again, is that if you put prior probability in every Kovac Liable neighborhood of F, then, if F's the true density, you will eventually concentrate your mass in the Hellinger sense. Hellinger neighborhoods are a little bit bigger. This is the Hellinger. Than the Kovac Liable. So I realize that, yeah.
Just wondering if there is a general conjugation between the two distances and whether the self-conjugate distances where we can show.
Not really. So it might seem odd that this Kovac Liable Hellinger, there might be some sort of more general thing about which topologies you need. I don't think so. I think this is just technical. There's no conceptual thing going on that I'm aware of.
So, are you always able to put non-zero mass on prior on every possible density?
Not necessarily. So is it possible to construct a prior such that I put positive mass around every Kovac Liable neighborhood of every density? Not necessarily. It depends what function space you're in. And one thing I kind of skipped over was there's another condition too, which is kind of more technical that I don't want to go into. It's about something called bracketing entropy of the prior, which also has to be satisfied. So it's a little bit more complicated. That's why it can be some work to try to figure out what's going on in this particular.
So does that mean that what would you say there? You're non-consistent on sets of measure zero?
Well, you're non-consistent on certain F's. It's hard to say measure zero because what's the measure you take? There are no measures on these sets except the one you're putting on. Right. So that's the easy case. Yeah, the truth is, I'm not going to go through the proof. The proof is actually not that difficult, as long as, obviously, if I could hand wave over one or two physical parts, that's not that difficult, but I don't think it's worth last time. What I want to do then, and I guess we'll do this on Wednesday, is finish up by talking about the more interesting thing, which is minimax rates of convergence. Even though we haven't done minimax yet, you've heard us mention it maybe. And when we talk about, I'm going to talk about the regression problem and show you that a curious thing happens when we start to look at the rates of convergence. It's just quite curious, quite interesting. So we'll do that, catch it on this project in a few minutes, and then Ryan will start doing the concept optimization. Any questions?